Good afternoon and thanks for joining me. My name is Natalie Collar and I'm presenting today on behalf of Whitewater Engineers in Denver and Colorado School of Mines. This presentation recording is for the 2021 annual CASFM conference, but it's virtual this year and I'm pleased to be able to join. As of the date of this recording, I will not be there during the actual conference, during my presentation slot. That might change, but if I'm not, I'll give my email address at the end of the presentation slide deck, and please feel free to email me with questions or follow-up comments. Today's presentation is titled Post-Fire Hillslope Runoff and Erosion Reduction Treatment Effectiveness and Inter-Study Variability. And that's a mouthful, but what we're getting at here is what treatment types are working best around the world after fires to reduce the runoff and erosion amplified responses that we typically see from landscapes after burns. And not always are we seeing higher runoff rates and sediment yield loading rates, but we often do. And there's quite a bit of effort that's put into controlling or mitigating that hazard after a fire. So that's kind of the impetus and background for this study. And the last thing I'll say about this slide is that Pitkin County funded this study. This was a study that was conducted throughout 2020, and it was funded by a Healthy Rivers and Streams grant. So big thanks to Pitkin County and the board of directors for that particular grant program. They've been really supportive of this research initiative. Also, of course, to Whitewater Engineers. I've been with Whitewater for just under 6 years, and we often operate in that post-fire hazard assessment realm and risk reduction mitigation prescriptions. So this presentation sits firmly within expertise that we have, but that we're also working on increasing. And then lastly, I'm a PhD candidate at the Colorado School of Mines in the Department of Civil and Environmental Engineering. My advisor is Dr. Terry Hogue, and the Hogue Research Group also focuses quite a bit on post-fire hydrology and geomorphic hazards. So this initiative is really well-rounded by a group of people that have expertise in this area, and we're excited to share the results of our study. So this will make up the first chapter of my dissertation that I plan on defending either late 2020 or early spring 2022. All right, an overview of what we'll talk about today. Just a quick technical background on how fire impacts the landscape and why that's worth thinking about mitigating. So what are the hazards and values at risk that we care about? Motivation for this particular project. Approach and methods for the study that we'll be talking about today, results, and then if I have time, I'll talk a bit about application of results and next steps. So as mentioned, this initiative was funded by a Pitkin County Healthy Rivers grant that was proposed and won jointly by Mines and Whitewater in late 2019, and the research was carried out in 2020. We've drafted our study up into a manuscript that's on its third review now, and we hope it'll be published soon. We'll share results when it is, but the name of the manuscript as it stands now shares a name with this presentation title. And I'm going to talk about what the goals of the study were in just a second, but some background about fires. Right now, this is the fourth presentation in CASFM's 2021 fire circuit, and fire's a big headline these days. Fire activity is increasing, at least relative to the 1980s when we first started gathering satellite measurements. We know that acres burned are increasing, but perhaps a more prevalent and relevant measure of fire activity and if it's problematic or not is the fraction of area burned at high severity. And numerous studies, including the one shown on this screen, show that the fraction of area, so acres burned every year, and this is for the Western United States, is the fraction of that burned area burned at high severity or high burn severity, typically soil burn severity, is increasing. And that can pose hazards, certainly hydrogeomorphologically, but also to aquatic ecosystems and many different facets of human health and safety. So here, this study by Parks and Abatsglow, excuse me if I butchered that, they're showing that using the send slope estimator, which It's a statistical test that looks at trends over time. We're seeing positive, significant trends in both annual area burned and annual area burned at high severity, and they're seeing these trends across numerous different fire-prone ecosystems, including the Southwest, where I guess the Rocky Mountain region is categorized in these plots. So seeing more area burned at high burn severity. And that is definitely a problem when we think about interactions at the wildland-urban interface, or the WUI, and that's a term that most of you have probably heard. The WUI is the boundary between undeveloped and developed land, where we have developed areas abutting undeveloped, often forested, but sometimes shrubland ecosystems. And in Colorado alone, and given that this is the CASFM 2021 conference, the WUI is a really important place, because 40% of our population back in 2010, when this with this data set was gathered, that's published in the study sourced at the bottom right of the slide, 40% of population in Colorado live either at the interface, at that boundary, or in the intermix, which is more dispersion of developed areas into undeveloped. And that's a problem for a couple reasons. And the first is that undeveloped areas often tend to be more fire prone based on the type of vegetation that's comprising undeveloped areas. Of course, that depends on your ecosystem. It's a lot different up in the Pacific Northwest than in Arizona. But we will have often more dense vegetation, especially with forest densification following 120 years of fire suppression efforts. We're also seeing aridification with climate change. So we may be more fire prone in undeveloped areas. So just on the inside of the WUI. And then it's also harder to suppress fires once they've started in the WUI because of access issues. It's often more expensive to treat areas in the WUI because of, again, access and difficulty of ease of access, and also treating the chronic landscape modifications and that chronic hydrologic and geomorphic risk that's posed after a fire. That can be more difficult in the WUI. So there's a few different reasons why thinking about WUI and fire interactions in it are important. So what's happening with fire and the alteration of the landscape? I'm just going to blow through this really quickly because this is probably information that most of you have heard, but fire affects landscapes differently, and there's lots of different factors that go into the variable landscape response that we've been recording over the last 100 years, and those might be topographic descriptors, topography, slope aspect, the type of vegetation that we have on the ground, the climate that vegetation is growing in. If we have a really wet climate with, let's say, low evaporation ratios, and we are, I'll say, climate hindered as far as ignition rates, that's going to act a lot differently than being vegetation limited and maybe the more arid high desert areas. Fire-induced changes to hydraulic soil properties, those can be many and can certainly drive the post-fire response. So again, a framing issue, or just a framing point for this presentation, is probably many that you've heard in the CASFM conference today. We're looking at that chronic post-fire risk posed by altered landscape processes that partition water in the landscape, not the acute risk of the fire event itself. All right, effects of some of these altered hydrologic processes: we might see reduced soil wettability, which really just means decreased infiltration rates due to generation of hydrophobic soil lens, destruction of soil biota, more rapid times of concentration. We might get more runoff with less rainfall. And then that runoff may, again, generate faster, and rates and volumes may be higher. And along with that, we'll often see increased erosion rates due to increased shear stress from deeper and faster water velocities running over hill slopes. Human health and safety is certainly compromised after fires. This is a picture I've shown in a lot of presentations over the last couple of years. It's taken from a helicopter in Southern California after the 2017-2018 Thomas Fire event, and that was really late in the season fire event in Southern California. These are in the San Ynez Mountains facing south at the Pacific Ocean, and we have Montecito here on an alluvial fan, and we had huge debris flows that were generated just a week or so after that fire was finally put out, and we had millions of dollars worth of damage. That red dotted lines show the lateral extents of a debris flow generated after that burn, and then a fairly intense pulse of rain following an atmospheric river. And there were 23 fatalities, I believe, after the Thomas Fire mudslide events. So certainly human health and safety is top of the priority list when we're thinking about post-fire hazard mitigation. Homes can be ripped off of their foundations. We can also think about in terms of water quantity and quality. You might see increased reservoir sedimentation rates from increased total suspended solids, turbidity in the water column, but we'll also see degradation of water quality. I'm from Paradise, California. That's a town that was almost completely burned down in the 2018 Camp Fire. That was California's most destructive and fatal wildfire, at least as of late 2019 was the last time I made sure those metrics still topped the charts. But in Paradise, we saw after thermal degradation of polyethylene pipes and HDPE pipes, we saw generation of BTEX. So thinking about your water supply system and what are the materials used in that system, are we going to see back siphoning? You can kind of spread contamination from back siphoning and depressurization. These are all really important factors for thinking about vulnerability of a landscape or a built system to wildfire fallout. All right, so now moving into the topic of the day, which is controlling that post-fire response. When we think about treatments and what our practitioners putting on the landscape to reduce risk, we can think about it from a top of the watershed to bottom of the watershed type of cascading treatment train. And top of the watershed, so where the hill slopes are burned, that might be source control measures to increase land cover. So we might see polyacrylamide that's put down. It's a flocculant to increase soil shear strength. We might see hydromulch that's applied either aerially or ground applications, and recipes for hydromulch can differ quite a bit, wood mulch, etc. But the point is source control, hill slope, land cover treatments typically for reducing erosion and runoff generation. And then moving down your watershed, conceptually, you'd move into the channel. So after you've kind of given up on controlling the source of the sediment, then you might try to increase its retainment rate up in the watershed, and you also might want to be protecting channel form and function. So for catching sediment, you may be using debris basins. For catching larger grain material or large woody debris, you'll often see debris racks installed, especially at culvert openings to just protect their drainage capacity. And then also things like stream bank armoring to, again, protect channel form and function. So kind of protect against hydromodification. And then maybe argue the most downstream, other than maybe specific building protections, but we'll often see road protection. So armoring and modifying drainage infrastructure so that you can maintain road access in burned areas. So of the case studies that this study identified, those with performance data are highlighted in pink here. So the goal of the study that was funded by Pitkin County was to look at what is being used where across the globe after fires, and then what's working best. So I did a comprehensive literature review to identify case studies and then extract performance data. And you can see that these pink treatment types are the treatments that were accompanied with performance data that we could use and analyze to look at performance efficacy. And almost every treatment type is a hill slope type of treatment. So that kind of top of slope source control measure. And that's not too surprising when you look at data published by Robichaud et al. In 2014. And I'll have references as the last slide in this presentation. But US federal government, BEAR, or the Burned Area Emergency Response Team, has budget to prescribe and in some cases implement treatments on burned federal lands in the US. And over the decades, you can see highlighted in red that Hillslope treatments, this is percentage of budget spent on Hillslope versus road or channel or public safety treatments, that it's almost always been Hillslope treatments that get the biggest cut of that pie. So that kind of comports with what the research efforts are showing us that I just summarized in that last slide. At least in the United States, we're putting a big effort on source control, and that makes a lot of sense. For case study selection, I did not put a filter on where in the United States a case study had to be conducted, but every red dot here is a case study that ended up being in that final data set that we ended up analyzing data from. And so you can see that most of the case studies, and we ended up with 34, most were performed in the Western United States, and then a handful in the quite fire-prone and well-known for it arid Mediterranean countries of Portugal and Spain. So we have a smattering of data sets in these areas. And I'll say that Portugal, Spain, and the United States, not just with data sets that are available, but kind of in the post-fire literature, I'd say that those three countries kind of reign on top, with Australia following. And then a data set, or I should say case study conducted in Israel and South Korea. So that's kind of the spatial layout of where researchers are putting efforts into post-fire monitoring. And then with these case studies, we extracted independent variables or potential explanatory variables into a big database. So we said, well, what controls treatment performance? Every data set is typically a paired treatment. So one of those red dots on the last slide would mean that there were a set of researchers that went out and they found a burned area. Maybe they were doing it in a laboratory on a hydraulic bed, but typically it was out on a burned landscape, and they found a control and a treatment plot, and they applied a treatment to the treatment plot and then measured runoff and sediment yield from those plots, and in that way looked at performance efficacy. So we said, what's controlling when a treatment performs well versus does not perform well? And that was one of the other major goals of the study. And we break out variable reporting rates in this database that we collected these variables in, just to see who's reporting what. So for example, 100% of these 34 case studies had detailed information about the slope of the hill or hills that were being treated, versus only 41% of the studies had information on the average annual temperature of the study area. So that would be kind of a gap in information reporting until our community is steadfast in what controls runoff and erosion reduction mitigation efficacy. We should really be reporting all experimental design variables in our publications. And then the other, so that's one takeaway. Then the other takeaway is the number of studies. So broken out by treatment type, here's the studies included in the analysis. If you're interested, feel free to pause the slide. But you can see that of the 34 case studies, and there's some overlap because not every study only reported on one type of treatment type, but we have the most data on wood mulch, and that's going to be important for a couple different reasons, but mostly with a certainty of results. We have the most data points on how is wood mulch, or surfaces that had natural material that was typically mulched on site from a burned area and then applied to the ground. How is wood mulch performing relative to, say, seeding? When you seed a hill slope, what does that do for erosion mitigation or runoff? Now we're seeing some data points actually plotted. This is the sediment yield data from the first post-fire year. Every bar is a case study data set. And just for example, this first bar is a hydromulch study. And you can see that north or up of the 0% means that there's a positive reduction in sediment yield. So this study showed that it might be 100% of the sediment yield that was being generated from the untreated plot was being retained in the treated plot. So this was a highly effective study in treatment type. And then you can go down the line and see that there's quite a bit of variability, and it's not too informative plotted like this, but maybe when you show, which treatment types are performing, what's the direction and magnitude of performance. You can start to see some patterns. But just look out here on the right side of the plot where we have a handful of studies that are actually increasing sediment yield in the treated studies. Organized a different way, you can start to see some real patterns in which treatment types are performing well consistently, and then which have high variability. So PAM, or polyacrylamide again, you can see high variability in performance, where most PAM treatment studies showed that application of PAM reduced sediment yield in the first year, but a couple increased it. And then the variability or efficacy of those sediment yield reduction iterations were quite all over the place, right? So one study just barely reduced sediment yield and another was up at 100%. Wood mulch, on the other hand, performance is really consistent overall. I'm just going to skip ahead. This is the journal-ready version of the data set that you just saw. So this is the same data. This again is that PAM data set, but you actually have runoff plotted on here now. So erosion reduction are the black bars, and then any study that looked at both sediment yield and runoff yield from a treated plot has a pair of bars. And you also see standard error plotted here now. So you can start to get a sense for where is inter and intra-study variability really high. And I'm going to skip through this, but needle mulch is a good example where you can see that every study of the 12 or so studies that we gathered in this research initiative reduced both erosion or sediment yield and runoff, but performance was pretty variable. And if you look under the hood, then you'll find in our 12 studies, there was a wide array of different needle types. And when we say needle, we're talking about the natural accumulation of typically evergreen organic material that falls after we have thermal damage of a tree. You get needle fall and it starts to accumulate on the ground, and that can protect soil grains against rain splash erosion and sometimes decrease soil clogging, etc. But the point is, for these 12 studies, there were pine needles from Japanese red pine, Canary Island pine, Aleppo pine, lodgepole pine, ponderosa pine, Douglas fir, grand fir. So high variability in the actual design of the treatment and the treatment type itself, and sometimes application rates. So it's not too surprising that performance variability was high. And I think that's one of the major takeaways of this study, is that standardizing I guess our experimental design is really important if we want to start getting multiple replicates to look at efficacy of different treatment types. We'll look under the hood more with PAM because of the extreme high variability and then the high instance of actual increases in runoff. So this is also a plot that you'll find in our paper once it's published, but this is the same, I'll toggle back and forth, this is the same data set that's highlighted in the pink box. Those are the PAM studies in post-fire year 1, just plotted with the different potentially controlling variables, such as, okay, was a study conducted in an evergreen or mixed forest area? Was it natural rainfall that was applied or simulated? So we can start thinking quite a bit about experimental design, including the PAM recipe itself, and if that had an effect on performance. All right, this is where the rubber meets the road. And here we have, it's actually, sorry about the header, it's actually sediment yield and runoff yield average % reduction over time. So this is the plot. If there was one plot that you should take away from this presentation, it would be this summary of data. And this is showing how many studies are conducted every year after a fire. So every column is the post-fire year, so years after fire. Moving to the right would be more years after a fire. And then in parens and italicized are the number of studies or data points that we have comprising the statistical summary statistic on the left. So we'll just take this first cell here, and what we can see is that there are 4 studies that were where data was collected in the first year after a hillslope was burned, and hillslopes were treated with hydromulch. And of those 4 studies, the average % reduction in runoff was 1%. So I'd say de minimis, especially given the high standard error, that's standard error after the plus or minus. For this hydromulch study, summary, we had a standard error that was orders of magnitude bigger than the summary statistic itself. So I would say that this is a de minimis and not statistically significant result, and that's confirmed by the non-significance of the p-value. We tested statistical significance with Wilcoxon rank sum tests, parametric due to the small sample size. And then if you go down below it, needle mulch, well, we had 13 data points. Results were statistically significant. Asterisks provide the significance level. Again, cross-reference down at the bottom of the slide. And we had a positive reduction in runoff of 20% with plus or minus 6. So that's a much more reasonable summary, and we have more confidence in these needle mulch results. But a couple things I want you to take away from this slide are that, one, we have way more studies and data points looking at sediment yield, so the effect of a treatment on sediment yield relative to runoff. And that's just, you can just count up the italicized numbers here and come to that conclusion yourself. Number two, we have very few studies, at least for runoff efficacy, looking at performance over time. So very little data telling us how runoff reduction is looking after the first post-fire year. Number three, that we are often getting much higher efficacies or better performance with sediment yield results than we are with runoff. And you can just back away from this plot and look at the colors. Darker green means greater reductions in runoff or sediment yield from treated areas. So you have a lot more dark green. Dark green indicates magnitude of the summary statistic. I'm just going to fly through this. Lastly, that wood mulch is by far performing best in the first post-fire year and then through time as well. We also ended up breaking out results by independent variables. So these are just summary statistics again, where you can see of all the studies that were, for example, conducted in these different elevation bands, which are performing best according to their median in the first post-fire year. So you can look at weighted average. Imagine these tables stacked on top of each other. Of all the wood mulch studies and all the straw mulch studies, etc., you can see that the weighted average median is highest for erosion reduction from wood mulch. And then moving down the line. But perhaps more telling would be to look at one specific attribute or landscape attribute like aspect, and that's the direction that the slope is facing. And you can start pulling out some big takeaways, like the studies that were conducted in northeast facing slopes, 0 to 90 degrees. They had the highest percent reduction in sediment yield the first year. And then on the 180 degree opposite quadrant of your compass rose, from 180 to 270 degrees, we had the lowest performance. We know that there are a lot of aspect-driven differences in vegetation, namely due to solar radiation, insolation, and soil moisture. But it looks like, at least with our data subsets, we confirmed that there is a difference in performance. And then lastly, you can look at Spearman's row correlation between treatment type and explanatory variables. What did we learn about controlling factors? And I'll say that for now, results are fairly inconclusive just due to a dearth of data. And that kind of runs into my last slide, or last couple slides. What do we plan on doing with our data set? And Whitewater manages and houses the International Stormwater BMP database. You can learn more about it at the link at the bottom of this page. It's actually now owned by WRF. So the International Stormwater BMP database is an effort to compile stormwater management BMP data to find out what's working best where, and incorporating a post-fire BMP module into the International BMP database, already a brand name that's well used, and many of you already know about the BMP database, would be a great way to kind of push forth our effort so that we can gain higher rigor and statistical significance in our results. So that would be kind of the goal, and you can start putting together data summaries like WRF has done, and with Whitewater's help with stormwater BMP performance. So thanks so much for your time. I welcome questions at my email address. This is a final summary of what we found, at least in the first post-fire year, with our runoff and sediment yield post-fire reduction treatment data. And here are references found on the slides. Thank you for your time.